So we know what is a Riemannian differentiable manifold, and we studied a few examples and basic properties and construction. So now, in fact, we could stay there for a long time. We could give a course on differentiable manifolds by themselves. But actually, the spirit of this course is to move to metric properties of these spaces, okay? So now, today, we introduce the notion of metric, of Riemannian metric on a differentiable manifold, okay? So what is a Riemannian metric? We can start right away with the definition. Well, we can phrase it in many ways. Depends whether you are, you know what is a tensor. I mean, it's something you build in algebra, essentially. Out of a vector space, you can construct a tensor algebra, the alternating algebra, and so on. So this actually would be useful and would make the language a bit more simpler in some sense, but on the other hand, it requires some structure that I don't want to use it now. So I have to use many words. If I could tell you, if I could use the words tensors, it would be three words. But what is a Riemannian metric? Now I have to say it in words. So it's a correspondent on M, of course, on a differentiable manifold. M is a correspondence which associates each point P in M an inner product that will denote by this or this. Okay? On the tangent space. But what is a bit delicate now to phrase precisely is that I want some kind of smoothness of these objects. Okay? So I want this to depend smoothly on the point P. Okay? So how can I say it? Because it is, of course, so what is an inner product is what? It's just a symmetric, positive, definite, quadratic form. Okay? So I mean, it's not a function. We don't know how to say it. It's smooth. So it's smooth in which sense? So smooth. But now the rest of this blackboard will be to explain the word smooth, what it means. Okay. So i.e. for any chart. So again, the trick. I mean, one way to say it is to pick a local chart. So if I take UX chart around P, okay, of course it's a local property, so I can just look around there, with coordinates x1, xn as usual, and where n is the dimension so with our usual notations, you see, they use it as usual. What do I need? I need the basis of the tangent space, and the chart does exactly this job for me. So I can look at ddxi at the point, strictly, it's actually in our notation, it's either P or x inverse of P. I mean, the notation is the same, whatever you mean. So if I take this inner product of two elements of the standard basis induced by the chart, everything depends on P here. I mean, The scalar product depends on P, and these vectors depends on P. They are moving around your manifold. So first of all, let's give it a name to these things, and I will call them like this. So these are functions, no? Because now if I fix I and j, this is a function. It's the scalar product, and so it depends on P here. So, but now I know what it means to say this is smooth. So if for any chart around P with coordinate is a smooth function, for any I and j, of course, for any choice of this basis vector. Okay. Okay, that's a long definition, but it says the most obvious thing you can require. No? I mean, everything depends smoothly on. Then, of course, in general, you will face the usual problem. I mean, how can I check that something holds for any possible chart if there are, because there are always infinitely many charts around the point? Well, but again, it's trivial now for you. We have seen these proofs over and over. If it's true for one chart, it's true for any chart. So you pick your favorite chart and you check whether this is true or not. Okay, so that's the problem of checking it. So this is just a way to measure the scalar product between tangent vectors. Now, you have never actually seen this, because having done Euclidean geometry probably for all your life, what was this? In the, let's say, example 0, if our differentiable manifold is Rn, and we are thinking of putting on Rn the usual scalar product, well, but the usual scalar product does not depend on P, that's the point. Okay? It's the same everywhere. Okay? So if you define the scalar product in Rn, and then you use it on each tangent space in the same way. So that's why you never felt the need of putting an index P in the Euclidean scalar product, in the standard scalar product, okay? Okay, so that's the... Now, having said what is a Riemannian metric, this automatically gives, again, as usual, same paradigm, the notion of equivalence among objects. So we know automatically what is an isometry, okay? So an isometry now, so now the objects that we are going to study are not just M, but it will be the pair. So from now on, in fact, a Riemannian, let me find the definition. A Riemannian manifold is a pair Mg. M, and now you choose your favorite notation. Either I put the brackets, or I prefer this one, okay? Where G is a Riemannian metric. Okay. So now among pairs, Mg, how do we identify? When do we consider them the same? I mean, so the notion, of course, is the notion of isometry. So given Mg and let's say Mh, so I take two Riemannian manifolds and the map and the differentiable map between them. Phi is called an isometry. So this, of course, first of all, it has to be smooth. Otherwise, I cannot even write the definition. So phi is an isometry if, okay, I need to compare, of course, it has to be a diffeomorphism. This will be actually, how can I compare the scalar product between two tangent vectors here and the scalar product of two tangent vectors here? So I need a rule that associates tangent vectors to M, from tangent vectors to M to tangent vectors to N, but that's exactly what the differential of the map does. So d phi p v d phi p w p phi p. Okay, so if I measure the scalar product of the image via the differential at the right point, at the image point, of two tangent vectors on n, oh sorry, I call them G and H. Okay, so this is H, because this is the target thing, at the point, I didn't say, yes, at the point phi of p here. Okay, so in our notation, now in this notation it will be this. This has to be equal to GP BW for any V and W in TPR. Okay? So it's not changing, a map which does not change the scalar product between the corresponding objects. Okay? Of course, you can extract out of this what is more usual to have, which is a local isometry. A local isometry will be a smooth map, which does this only on an open set. Okay, so in particular, this, you don't require it to be a global diffeomorphism. Okay, but that's, how to add the word local, it's, actually, out of this, you don't get automatically the diffeomorphisms, and so let's add it, and phi is diffeomorphism. Okay? If you drop this global condition and you require this property to hold only on an open set, you will call it a local isometry on this open set. Okay, so now having done surfaces, now all this is very fast. So, of course, so examples. I already said more or less in words what does it mean, the Euclidean space now seen as a Riemannian manifold. If you take Rn with, in fact I don't even have to say what, with the usual, with the scalar product that you have always used for in your life. This is one of these, of course. It has a very special property that it does not depend on P. Okay? That makes this and from now, so this will be called the Euclidean space. Very important and interesting class of examples. Riemannian metrics pass to subsets. Okay, so of course, as long as the subset is sufficiently nice to have a tangent space. So what do I mean by that? If we take an immersion, in fact more generally, so suppose f from M to N is an immersion. Remember, an immersion means it's differentiable and the differential is injective. Okay, so the differential does not have kernel. So in particular, remember, this can happen only if the domain has dimension less than or equal to the target. Okay, so it's something from small to big. Okay, so if you are in this situation and on the target, in fact, I can add it here. I have a Riemannian metric. And actually, the domain gets for free a Riemannian metric. How? We can construct a Riemannian metric on M, which we will call the induced metric. How? And we will denote it by F star H, okay, with this symbol up. How? Well, I have to tell you, so I want to define F star H, so this object here, at one point, P, And this has to be the scalar tensor applied to two tangent vectors. Okay, I need to make sense of this symbol here. Okay, as usual, there is only one way to make sense of this symbol, to manipulate these symbols. How? Well, you have to transfer the tangent vectors to the target, because that's where I know how to compute scalar products. So, I define it to be H at the point f of p, the corresponding point, of the image of the two tangent vectors via the differential. So, dfp v, dfp w. Okay? And then you see why I need an immersion, because actually this would make sense for any map. For any C1 map, I can write down this formula. But why is this a Riemannian metric? It has to be symmetric, but this is always true, because symmetric means if I change these two, I don't change anything, but this is the property required. This H has this property. So the symmetry is okay, but the positive definiteness is a problem. If this map, if the differential of the map has kernel for it, it's clear that this is important. You will never get a positive definite. Pick an element of the kernel twice, for example. You are computing the norm squared of something, so positive definite forces this to be positive. While on the other hand, if it's in the kernel, I get 0. Okay? So that's why I need an immersion. And now, then what else? I should check the smoothness, which actually required half of a blackboard, but you can imagine it's trivial, no? Because I need to prove that this depends smoothly on P. But everything here is smooth, and H depends smoothly on the base point. So there is really nothing to prove, okay? But now this is an extremely important class of examples. So basically, anytime you have an ambient space which has a metric, all the submanifolds get automatically at least one Riemannian metric, the induced one. Okay? So in particular, you can mix example 1 with 0. Now, Rn, the Euclidean space, is a Riemannian manifold. Anything inside Rn is a Riemannian manifold as long as it's a manifold, okay? As long as that does not have corners and so on, okay? So, for example, surfaces in R3 are Riemannian manifolds, okay? Or everything we studied in the first part of the course is a Riemannian manifold with the induced metric. Of course, to translate the language, and in fact, what is the induced metric on a surface in R3? It's the first fundamental form. It's just another way. The word first fundamental form will disappear forever, and it remains the induced metric from the Euclidean space. Okay. Okay. So, for example, all these examples are, I mean, all the submanifolds of Rn. Now you know automatically how to build. Okay. Now, okay. Any questions about this? This is just a change of language. I mean, we're just mixing kind of things that we have already used in different forms. Remember, I made an historical comment about the theory of surfaces. Basically, it's one of the few cases in the history of mathematics where you can actually write down a year where it was essentially done. I mean, in the sense that then, which was the year of Gauss' book on surfaces. You will see everything here in this story brings the name of Riemann. Riemann was essentially a student of Gauss. I mean, in a quite strange way. But actually, the reason why Riemann actually wrote about everything and did everything, even though he died very, very, very young, he wrote essentially only one thing about what we call now Riemannian geometry, and this was 1854. but by no means this has the same. So while if you take the Gauss book on surfaces, you can actually study it. If you just knew Latin, I recommend you to study on Carmo because it's written in English. You can actually study it here. If you take the Riemann's actually dissertation, it was a kind of an habilitation for becoming professor, essentially. He wrote a thesis on what we now call, actually the part which we now call Riemannian geometry is very, very few pages and very obscure. I mean, so people for almost 60 years, actually the picture became quite clear only around 1910, 1920, okay, and it was Hermann Weyl to write down really what we now, the way we study it now, it's really due to Hermann Weyl, okay. But it's also, it is always very interesting to go back to the roots, and there are of course translations of Riemann's work in English. It was in German, of course, the original one, and it's very nice because it's really obscure. Very hard to understand what he's really saying. And actually, there are even comments for which you understand that the history has taken this route, but it could have taken very different routes. It was not at all clear that, in fact, there is even a very nice comment, a very interesting comment at one point in Riemann says, okay, he was basically trying to define a manifold. And he entered into a very strange discussion about what a manifold should have been. The topic of the dissertation was physics. Right? It was and at one point said, okay, but this discussion is leading me to nowhere, but I have to discuss my thesis. So I have to choose the simplest thing now for time problem. I have to submit it. And so basically he gave the definition of manifold. So it would be quite interesting to go back and say, well, suppose you had one more year to write your thesis. I mean, maybe mathematics would have been completely different. I mean, it's anyway, a little bit of history. Now, of course, in fact, before going into what do we do with the Riemannian metric, which of course we measure lengths of curves, we measure areas of domains and so on as usual, as we did for the first fundamental form, there is a foundational question. I mean, passing from the class of differentiable manifolds to the class of Riemannian manifolds, I mean, is it a condition for a differentiable manifold to have a Riemannian metric or not? You see, every time you put a structure, you take a set and you want to define a topology. And then you ask, but does every set have a topology? I mean, the set of topological space, is it smaller than the set of sets? I'm making many tautologies, okay? And then, of course, the answer is no, because you can put the trivial topology on any set. Okay, then you say, take topological manifolds. Can you always put a differentiable structure? I mean, every time you define a structure, you need to understand whether you are restricting the class of objects that you are studying. Okay. So now we pass from differentiable to Riemannian. So the obvious question is, okay, but does every differentiable manifold have a Riemannian metric or not? I mean, are they fewer than differentiable manifolds? So let's face it, because actually the answer is quite interesting, because the answer is no. Any, in fact, let's state it as a theorem, but it's actually the proof, which is quite interesting. So any differentiable manifold has at least one, and of course once you have one, you have infinitely many, okay, but at least has at least one Riemannian metric. Okay, so how do we prove it?
Can we bring it from Rn using chart?
Exactly. The idea is bringing it to Rn because you say, okay, Is it a local property or not? Because now the philosophy is everything which is local on a manifold, it's okay because I'm putting the local structure of Rn. But now having a metric is not exactly, it's a mixture of local and global. Okay, because if I pick my manifold, and if I pick a chart, so since this chart comes from Rn, and by the example 1, no? In fact, I could use example 1. After all, the map X is an immersion from U to the image of U. Okay? Well, actually, I should do it the other way around. No? I should do it with X inverse because I want to define something here, but clearly I have something here because this is just a domain of Rn, so it has the Euclidean metric. So I can import, for example, the Euclidean metric on this disk here. Okay, so locally it's okay. But now, if I have two of these charts, and I keep on playing this game, I have a problem. Because how much is the Romanian metric here? Well, is it the x1 or is it the y1? Well, and of course I don't know. And in fact there are infinitely many in principle. So either I prove that by some incredible miracle, which does not happen, they are the same, which is impossible because actually I can change it. I can change x and y essentially the way I want. So even if it was true for something, maybe it's not true for the font thing. Or this idea doesn't really work. But it's not completely wrong. So how do we adjust it? Well, take an atlas of charts. Let's give it a name. U alpha, X alpha. And what can we do with it? Well, actually, one way to solve this problem, actually maybe you can get to the answer, because one way to solve this problem is that, okay, since I don't know which one to pick, the x1 or the y1, let's take the sum of the two. The sum is something, the sum of positive definite quadratic form is a positive definite quadratic form, so that looks like a good idea. But what is the problem? Well, so in this way, the sum becomes irrelevant. I mean, it takes care of both, so it seems okay. So what is the problem? Why I cannot take just the sum of these two? Because of course the sum of these two will not be smooth. No, I mean, here there is nothing. Here there is only one. Then you jump to the sum of these two, and then you go back to the other one. So here is the smoothness property which seems to create problem. But that's actually why I bother you 10 minutes with the partition of unity. So suppose in fact that this atlas is in a position to apply the partition of unity theorem. What does it mean it's in the position? It's a locally finite, no? Locally. So that for any point I have only a finite number of them. And take, I think I call it phi alpha or f alpha, whatever you want to call it. F alpha, the associate n, actually the partition of unity is never unique, but I mean n associated partition of unity. Okay. And in the way I told you what is a partition of unity, I've been a bit, I mean, I gave you in fact even more information than what we really need. Remember, a partition of unity is a collection of non-negative functions. Okay, so f alpha F alpha means, this means F alpha is a function from, in our language, is X alpha of U alpha. To R, which is non-negative for any alpha, and the sum is equal to 1. I gave you a very refined version in terms also of the supports. Oh, yeah. Sorry. In fact, F alpha in principle is a function from M. Every F alpha is a function from M. But actually, here I could list as a property the fact that, so if I, let's say F alpha goes from M to R, but then the support of F alpha is contained in X alpha of U alpha. Okay. So outside the chart that I'm looking, the alpha chart is 0. Okay. Okay, if I have this, then it's game over. Okay. Once I set to one notation. So now I can define okay, if I pick a point, I pick any point P. So P is now a point in M, and I take two tangent vectors at this point. So I need to define G P of UV. Okay, this is my mystery object. I'm trying to define a Riemannian metric. So for any P, I need to define this with all the properties I want. Okay, so define this to be the sum . So let's write it completely. So this is the sum over alpha of F alpha of P times so every time this two tangent vector stays inside, so I need to take x dx inverse alpha of U, dx inverse alpha of V. And now the point is that you see here, I don't have to say at which point. So what is this? This is, if I take a tangent vector in M, I send it back with the differential to the tangent space to Rn, and now by this symbol, let's agree that this symbol without index is the Euclidean one. Okay? So I don't have to tell you at which point I computed, because it's the Euclidean metric is independent of the point. So I do the Euclidean scalar product of the corresponding things. Okay. Okay. So now you have everything to check that this is a Riemannian metric, and this solves the problem of smoothness, because altogether they are. You see, first of all, you have to check it makes sense. But this is the locally finite property. No? Every point lies only in a finite number of them, so this sum, which a priori is an infinite sum, it's only a finite sum of objects. And then all the other properties tells me that everything is smooth. Okay. So it actually looks like a trick. Well, it is a trick, but it's a very smart one. Okay.
Can one use a kind of a trivial method?
You see, but that cycle. So this ends the proof. But actually, every time you see this proof for the first time, I think every student, in fact, sometimes even later in life, you start thinking, well, but that means that maybe I'm importing the Euclidean metric on M philosophically. Yeah, but this is one moment where philosophy is just confusing, because that's not. I mean, it's like saying, well, this makes this disk flat, for example, in some sense. Well, that's completely wrong. The metric that is written there in general, I mean, of course, sometimes it will be true, but in general, if I computed a point P and if I computed a point Q, even inside the same thing, they will be very different. I mean, this is not, I mean, in fact, it doesn't even make sense to ask, but even if there was a sense to ask, this metric is not the same at P and Q. I mean, you say, okay, but P and Q would be 2 points here, and then taking really the Euclidean metric. But no, because maybe, in fact, there has to be another chart touching one of these and not the other or something like that. And then this will change. You see, it's where everything boils down to what are these functions here. And these functions are not, or at least very rarely will be functions like these. I mean, there will be a part of it where, in fact, it's not even clear. I mean, this is really a number of things which help each other to become of some one. Okay, so this metric will, in general, never be flat.
But my question was different. My question is, if we take at every point the trivial inner product, I mean, the inner product of two vectors is 1 if the same vector with each other and 0 otherwise. I mean, I fix a metric at all points and I make it trivial. The sense is that trivial in the sense that the inner product of two vectors, if they are the same vector, it is 1, unless of course it is 0, and if they are different, it is 0.
I never heard of this metric, and now I have to think, because my first reaction is that this is not a metric. Let me think. A metric for which the scalar product is 1 if the metric is if the vectors are the same, and 0.
Unless it is the zero vector.
No, but I strongly doubt that this is linear, no?
Yes.
I mean, this is not a bilinear.
Yeah.
Okay, this would be a very weird thing. Okay. Anyway, I try to convince you that of a problem. I mean, it's easy to see that this defines a metric, and this is more psychology. I mean, that this does not make anything flat. That's the point. You are importing with these partitions of unity the flat metric of Rn, but actually this, in general, will not have any interesting curvature problem. But okay, but the fact it's interesting. So any differentiable manifold is a Riemannian manifold. So passing from differentiable to Riemann is not restricting the class of objects that we are studying. Okay. Now, okay, now let's face another a beautiful but a bit delicate problem. We need well, it's a bit difficult to justify at this moment, but one of the key operations that we did for even on surfaces on R3 was to take a two vector fields actually, or one vector field in some sense, and to take the derivative of one vector field in the direction of another vector. So since a vector is a direction, and I'm thinking now of a direction as a linear operator in the sense something that takes something and gives me the derivative in this direction. I know this is tautological, but what is a direction? The direction is really what gives you the derivative in that direction. Okay. So a crucial operation, this is just a mixture of algebra and analysis, is to take two vector fields and take the derivative of one vector field with respect to the other. Okay, and this was leading to many interesting things. Okay, this was a basic operation that we did a few times. Now, okay, we want to be able to do something like this. So we need to have kind of a notion of derivative of a vector field with respect to another vector field. Okay, and that's a bit delicate, because you see, what is the problem? Again, why in Rn we didn't notice that this was even a problem? Because in Rn, if I want to know whether a vector field, so now suppose that at every point I have a vector, okay, on your space. Now, of course, the notion of derivative is related to how much is this vector changing in a given direction. So, and the whole point, so how do I measure if something is changing? I take this object at this point P, I move it a little bit, P plus TH, I could do this even for the derivative of a real valued function, okay? So what is the derivative? It's when you write down the notion of f of x0, I mean, f prime, what is f prime of x0? Is the limit, no? Think of the definition of what it is. As h goes to 0 of f of x0 plus h minus f of x0 divided by h, if it exists. And even for vectors, for vector fields, you can say what is the derivative of vector field will be kind of, again, a ratio, no? The difference between the value at two different points in a given direction divided by, okay. And you see here there is a very highly non-innocent thing that you are doing. You are taking the difference of the object at two different points. So, of course, if these are real numbers, I'm taking the difference of real numbers. If these were vectors, okay, now imagine this for this general formula. If these were vectors, well, if I'm in Rn, I know what it means to take the vector at a given point and the vector at nearby points and take the difference. Because in any case, the tangent vectors to a surface were actually vectors in R3. So I use the R3 structure, I take the difference and I do whatever I want. But now that's exactly game over. Now we are on a differentiable manifold. If I want to define the derivative of a vector field, for example, in one direction, how do I compute, in which sense do I say that this vector has changed between the point P and the point Q? Because the tangent vector fields will be so x of P will be in TPM, and x of P plus TH, or whatever you mean by that, will be in TP plus TH. So what do we mean? What do I mean that these two things are the same? In fact, even what does it mean to be constant? Because there is no general way to compare, to take a vector here and compare it to a vector here. I mean, these are finite dimensional vector spaces. So you can say they are all isomorphic. But then everything would depend on the choice of the isomorphism that you take. You see, I think that's actually the moment where you really realize something that, at least for me in algebra, has always been the difference between two things being isomorphic and two things being canonically isomorphic. Okay? And in fact, you realize that actually being isomorphic is really not interesting. It's the canonical, and here, of course, these two things are isomorphic because they have the same dimension. But they are not canonically isomorphic. Any isomorphism would depend on the choice of a basis. That's really, but then I can make anything constant if I want. If I'm sufficiently smart in choosing the isomorphism, anything would be constant. Okay? So if I want to say, well, this vector is not changing, this has to be something a bit more intrinsic than this. Okay? Do you understand the problem? Because actually the answer is a bit, it's beautiful, but it's a bit delicate. Okay? So we are facing this problem. If I want to build the notion of derivative of a vector field, I need to face this problem. How do I identify vectors from here to here before doing something like this? Okay? Very good. Because actually, now I give you a little bit a big answer, because in fact the answer is a bit surprising, because in fact the answer is that there is actually by no means a unique way to solve this problem. Okay? And this, anytime you solve this problem, it means you have constructed what is called an affine connection. So let's do, it's convenient to have a symbol for the space of vector fields. So let me call it something like this, xm space of vector fields, smooth vector fields. On M. Okay. And actually I remember things as notations. I think we already used this notation here. D of M, This is just the module of functions of smooth functions. Okay, so these are two notations that will make something a bit. So what is an affine connection? Affine connection is a map, and affine connection is a map. Okay. It's a solution to the problem. So now a solution to the problem was, how do I take the derivative of a vector with respect to another vector, because the direction is another vector. So in fact, first of all, this is the symbol. An affine connection is, we use the symbol of the gradient. Of course, there is a very good reason for that, and we will see it. So it has to take two vector fields. One will be the one that you want to differentiate, and the other one is the one which tells you in which direction I'm differentiating. And the output is what? Whatever you do, the derivative of a vector field has to be a vector field. Okay, so it takes two of them and gives me another one. Okay? But of course, no, now I do it a little bit axiomatically. I mean, so of course, in order to call it the derivative, it has to satisfy a few properties, otherwise we don't want it to call it the derivative. So in fact, symbol, so it takes two vector fields and gives me another one, and the other one is denoted by this. So you are taking the derivative, we decide that the second one is the object that we are differentiating, and the first one is the direction in which we differentiate. And we distinguish them in this way by this symbol. Okay, but such that, I mean, not anything will work, so of course we go back to Rn, we take all the properties that we think are crucial, no? And we put them now as axioms. Okay, that's the typical thing. So which is the first property. So what does it happen? In Rn, of course, what is the critical thing is that vector, you can take the sum of vector fields, and you can take a vector field times a function. Okay? So, what does it happen to a vector field if you take, don't be confused, f and g, so g is not the Romanian metric. So if I take two functions, so now of course, in all these notations, f and g, and I don't think I will need more than two. Yeah. So f and g are functions. So in my notations now, these are here, and x, y, and z are vector fields. I don't think I need more than two again. So these are no more than three. So I put them. So okay, in Rn, what does it happen? If you take the derivative of a vector field in the direction that you can split. In fact, I mean, let's think for a moment. What is the effect of taking the derivative, not of in the direction f, but now you multiply by a function? So that means that the direction of the vector that you are using as direction for the differentiation is not changing. It's just the amplitude which is changing, no? Because f of x has the same direction of x, but it's just of a different scale. Well, go back, think 3 seconds, you know what it happens. It's the same thing, it's the same without f multiplied by f. I mean, because actually the derivative depends really only on the direction in terms of, okay. So what, and now we put it as axiom. And also, what is the effect of taking the sum? Actually, it's taking the sum of the derivatives. So, okay, so this we want. It seems like a very basic. So, and this takes care of all possible algebraic operations I can do, more or less, in the first variable. What about the second? Well, now you would like to say, well, what does it happen if you take? So, I mean, eventually I would like to write down what is this in terms of the other thing. And now I realize there is a problem. Well, I mean, I want to be a problem, because think of in Rn, what does it happen if you take the derivative not of a given vector field, but of something multiplied by a function. Well, this function enters into the game because you want some kind of Leibniz rule. So it has to be the derivative of f times y plus f the derivative of y. Okay? It has to be something like this. Okay, so let's phrase it properly. And now what does
f with respect to x?
Sorry?
To differentiate f with respect to x?
Yeah. So now the question is, what does it mean the derivative of f? But x is a vector field, so f in fact is a linear operator which takes a function and gives me a function. So no problem actually. So this is x of f times y. You see? Plus f nabla xy, and then plus x of g times z plus g nabla xz. Okay? So I want it to be linear in the sense of the sum, and Leibniz in the sense of multiplication by functions.
Are we assuming it is linear in the second component? Or?
Sorry?
Is it linear in the second component?
What do you mean linear in the second component?
Yeah, in this, no, I mean nabla x, y plus z. Is it nabla y?
Put f equal to 1 and g equal to 1.
Okay.
These are functions. I mean, real numbers are functions, constant functions, and of course they die because the derivative of a constant is 0, the derivative of a constant is 0, so if and of course this will be 1, so if you are just asking what is the derivative of y plus z, well, that's the sum of the two derivatives.
But if we assume it is just linear in the sense of constant, and this satisfies the Leibniz rule, f x, it doesn't, this second one doesn't follow from these two assumptions, right?
No.
Okay.
No. Okay. Okay, so this is what we, at least we definitely require from something in order to be called enough. I mean, so an affine connection is actually, you should really think of an answer to the problem of what it means to be a derivative. Okay. So, again, as usual, let's analyze a little bit on a chart. What do these properties, I mean, now it's just introducing notations. But if I add a chart,
Excuse me, but what is affine about it?
oh, affine, it's kind of remembering this, in some sense, because this object, because it is defined on spaces where it makes sense to take sums and so on. So it's like, it's a little bit like saying it is linear. It's a linear connection, okay? Because it behaves nicely with respect to the vector space, okay, structure. There is a much more general picture behind all this, where the objects do not move on a vector space, but for example, they move on groups. And then you would have a different notion of, but I mean, so there are generalizations which have been very important, especially in theoretical physics and so on, where there is no affine structure anywhere. So just to remember, so this is just a way to remember that you are doing the standard geometrical thing of the tangent space, okay? So now, in a chart, what does it mean to know or not know an affine connection? Well, in a chart, of course, I can take x and y, and write them down with respect to the standard basis associated with the chart. So that means x will be, remember, the sum this is very bad, AI ddxi, okay, and y, let's say, will be bj ddxj, okay. For some choice of functions, A, these are functions, A and B, no? Because these are really vector fields. So if we put properties 1 and 2 into the game, we can, so nabla xy, so property 1 will take care of putting a linear combination with smooth coefficients in this place. And this will tell me automatically what it gives, because this is going to give, so everything is behaving in the simplest way. Everything goes out, the linear combination goes out, the coefficients goes out, and I'm left with nabla ddxi, well, and now of y. But y now I have to look at here. So let me first write it, sum over j, bj, ddxj. Okay, so this is what? This is the sum over I of AI. Now I have to be, careful. I mean, I have to satisfy a Leibniz type rule. So BJ's are functions, so they need to be differentiated. So any of this thing appearing in the sum will produce two elements, no, in the new sum. So this will be the derivative of the bj, so ddxi of the function bj, okay, times ddxj. Because this is the effect, I mean, this is the old-fashioned derivative, but this is actually the effect by definition, if you want, is x of f. Okay. Plus bj, and now I'm left with okay, so anything now it's still but what is this computation saying? Says that, well, if you knew basically the notion of an affine, the knowledge of an affine connection is all contained, of course, as you expect, in the knowledge of the action of the affine connection on the basis. Okay, so if I knew this, I could write the action on any vector. So not surprisingly, I mean, I'm basically requiring some kind of linearity, you know. So usually we write down, we give names to these things. So when you do computations in an example, you focus on these objects here. So the actions over, what are they? So if I look at this object here now, the only thing I know is that this is just another vector field. So the only thing I can say is that this must be a linear combination of the elements of the basis. Okay, so this must be something, a linear combination over k of ddxk. Okay? For any choice of I and j. So okay, the notation is not very friendly. It's the coefficients have been called gamma, I and j. So they have two indices here, and one, because this is the one that you sum, okay? And these are called the Christoffel symbols of the connection. Okay. You can think of everything you know in Rn and try to repeat. So suppose you are doing nothing. Suppose you are doing the classical thing. Now these were properties, I mean we put them as axioms, the properties of the standard differentiation of vector fields in Rn. So if you keep on thinking, so the standard differentiation in Rn is an affine connection, of course. I've built the definition based on that. Okay. So what are the Christoffel symbols of the standard affine connection of Rn? Well, that means in Rn, if I take the vector field ddx and I take the derivative with respect to ddy, how much do I get? 0. So the Christoffel symbols of the standard connection in Rn vanish, all vanish, for any I, j, and k. Okay?
But if I is equal to j, I will get 1.
Oh, sorry, yeah, well, yeah, you're right, except II, which, what will survive for II?
I. This 3 must be the same, I think.
And you get 1. Okay. So, okay, this is just, I mean, whatever we say for affine connections, you can play this game in your head, okay? But what are we really generalizing? Okay. Now, the problem is that there are, on a differential, well, the problem or the beauty is that there are, in general, and this I will not prove, infinitely many affine connections on a differentiable manifold. And there is absolutely no way to decide which one is better than the other. And this is a bit surprising because you think that the notion of differentiability, the derivative, should be somehow natural. And actually this makes you understand that no, there is absolutely nothing natural in what we have always called the derivative. Okay? So in principle you could imagine a completely crazy world where the derivative is something completely different. Okay? Of course, if you just require these two things. So the reason why in Rn we never had doubts is that in fact there are extra properties that you impose on that you find that the standard derivative has that are not here. Okay? But actually, they depend mostly on the compatibility with the metric. So you see, these are things I can define on any differentiable manifold. Here, there is no Riemannian metric. If you think one of the most beautiful property of the differentiation of in Rn is that how it behaves when you take the derivative of the scalar product of two things. Okay, so let's see if the manifold was actually Riemannian. What is it natural to ask? So remember, in Rn, which was we have used it, you have used it millions of times already. If you have two vectors which depends on one parameter, which if you want is just a vector field along a curve, for example. Now, if you have two vectors and you are taking the scalar product of this and you are asking how much is d in dt of this. No? After all, this is the derivative. No? And you know that this is actually the derivative. I mean, also the scalar product behaves like Leibniz. No? It's the derivative of the first times the second plus the first derivative of the second. Okay? Now, this has been fundamental every time. Okay? So let's see. First, I should have give you another definition first. So every time you have an affine connection rules out a very special class of vectors, of course. I mean, because it's a derivative, of course, the simplest thing that the derivative does is that tells you which are the constants. No? The derivative, if you say derivative 0 means constant. 0 everywhere, not just at one point. I mean, suppose that you have something whose derivative is 0. So, Not sure if I want to say it now or I'm just confusing. Okay, yeah, let's see it now. Suppose, let's face it for a moment, this one. So suppose you have your differentiable manifold, and now you pick a curve, gamma, on your manifold M. Okay. Now, in fact, you don't even need a vector field along M, but in principle, for what I'm going to say, you could actually have a vector field along just the curve. Okay, I'm not requiring, of course, the vector to be tangent to the curve. At every point of the curve, I'm taking a vector field which is tangent to the manifold. So it can point outside to the curve, otherwise there would be only one. Okay? So a vector field V along gamma is called parallel here. I want to be a little bit sloppy. I'll tell you also where I'm slopping, but it's called parallel if nabla gamma dot V is constant. So if I have a curve, I have one very special vector field along the curve, which is the tangent vector to the curve, gamma dot. Okay? So what here I want to formalize the notion of a vector field which is constant along a curve. Okay? And the only thing really, it's out of frustration. I mean, the only thing I can really say is produce the vector field gamma, the tangent vector field, and now I have a notion of derivative, and so I say, well, if the derivative is constantly equal to 0, in some sense I want to say that this is a constant vector. So instead of constant, we say it's parallel. Because actually there is nothing constant about this vector. Okay, because you should not fall into the trap of thinking that something which satisfies something like this, you can write down in charts. Actually, let's play this game here, since we have the formula. I didn't erase the formula yet. V is one of these. In our language, it's the y vector, is the one we are taking derivatives from. No? And gamma dot, well, is just the vector, is the tangent vector, but decomposed with respect to the basis. No? Now, imposing that something like this is 0, so you see, this is nabla xy. Now you put, okay, this equal to 0. You can actually use also this expression here. If you want, I could have added another line to express, because I write it down in terms of the basis ddxi. And then, of course, a vector is 0, since this is a basis, if and only if every component is 0 with respect to this decomposition. So pick, now here, of course, I would have written ddxk, and here there was the ddxj. Of course, you have to change names. You call, for example, here in this part, you call this index k. So, and then you take the k coefficient. You say, okay, the k coefficient equal to 0. What is it saying? It's quite a complicated equation. No? I mean, I don't want to, there's nothing, I mean, if you want, we can write it down. It means I have to call this index k, so this means this is the sum over I of ai, dbk, dxi, well, I don't write the ddxk because this is the coefficient of the ddxk vector, plus bj, or sum, well, this will be again a sum over j, so in fact I can even call it, well, okay, plus sum over j of bj, gamma k ij, and that's it. Okay? So suppose I'm saying, well, and what are the conditions? The conditions are, so x is the tangent vector to the curve gamma, so somehow the a are given. You give me a bunch of a of t. And you are saying, well, what does it mean that the vector b, the b vector satisfies this kind of equation here? Well, for sure, you can imagine this has nothing to do with the fact that the b are constants. In some sense, but you see, this would be y is constant. No, because I'm saying nabla xy is equal to 0. So you might say, okay, a vector field will be constant, whatever that means, if and only if I write it down in a system of charts, the components are constants. I mean, that would be an obvious guess. I mean, a very naive but obvious guess. And then you write it down and say, no, but this has nothing to do with it. It works, so how come in Rn it's true? In Rn it's true. What is a constant vector is a vector whose components are constants. Well, precisely because these were 0. So then you are left with the equation derivative of the component equal to 0. Okay? So that's why it's better here not to put the word constant, just to try to avoid confusion. So something has 0 derivative on a given curve means it's parallel. It's not changing, but it's not changing not in the sense that the components are constant. It's not changing in the nabla sense. Okay? Okay, so this is a vector a parallel vector field. Oh, sorry. Yes, it's a parallel vector field. And then now I can add the most important definition, because now that I know what it means for a vector to be parallel, I can say if on a Riemannian manifold MG.
Excuse me, but what here nabla means, because to use nabla we need our vector field to be over all of the manifolds, not on a...
Okay, yes, I forgot to tell you. I was saying I've been a bit sloppy, and that's exactly the point where I'm being sloppy. But I don't want to lose 20 minutes to solve the problem of the fact that gamma is defined only along the curve gamma. While all these things require the vector field at least to be defined on an open set. I mean, in fact, here it's required to be defined over the whole of M, but at least on an open set. Okay. So the first thing you have to do is to take this vector field, extend it, find any extension on an open set of the curve, and then do that. So in principle here there was a jump. You see? This is not defined over M, or not even on an open set, while all this story applies to those. So what I need to do is to take this vector, extend it, so find a vector field on M whose restriction on the curve is exactly this one.
Is it always possible?
Then apply this story, and then restrict everything to the curve. Okay? So now there is only one problem. Is it always possible to extend gamma dot to an open set? Locally, yes. Globally, no. Okay, so you can start construct monsters, completely useless, but they exist, so you cannot claim in general. But what do I mean, locally, yes? That if I take a sufficiently small piece of my curve, then it's true, and it's true even here, wherever I am. It doesn't matter if I'm very close to the origin. If I take a little piece of this curve, there will be an extension. Okay? So on a very small open set, but that's okay. Then I can use the theory. So it's really one of the situations where you cannot say what you think because it's wrong, but it's essentially true. Okay? And that's where I don't want to enter. Okay? Now, so what does it mean now suppose that your manifold is more than differentiable, it's Riemannian, and nabla affine connection. So using the undifferentiable structure, I have an affine connection, and now I want to add some compatibility between the affine connection and the metric. So the most natural thing to ask is actually that every time, so an affine connection is called compatible with G if for any gamma and for any choice of parallel vector fields x and y parallel on gamma, G of xy is constant. Okay? Okay, we are moving on a delicate subject. Okay, so we are saying now all this story is telling me what it means, what at least should I call a constant vector, even though you see if I drew it, it will be changing quite a lot. Okay, but now I know what it means to be parallel. And now the compatibility I require is that if I take two parallel vector fields, the scalar product between them doesn't change in time. This actually, you see, if in the classical case, what was going on? If they were parallel, but now parallel in the classical case means they actually don't depend on the components are constants. So if I take the scalar product and I take the derivative, I get 0. Okay? So this seems obvious in Rn. So the usual differentiation satisfies this property trivially. But now we have to impose it. Okay? And now, so now the question is, do they exist and how many compatible affine connections? Okay, and actually I think this is exactly the moment where we should stop. Actually, there is still one subtlety we have to face, because actually, as said in this moment, it's not true that there exists. Or, of course, we are aiming at a theorem that says there is one and only one. Okay? It is still not true. So, okay, next lecture we will see what to add and then to prove that finally the things will be uniquely defined. Okay? Okay.